A mobile request enters a tunnel, changes networks, and loses a few packets. With a traditional TCP connection, that small disruption can delay unrelated work sharing the same connection. Java 26 gives backend applications a new option. The standard HTTP client API can now speak HTTP version 3 over QUIC. The same release also changes how Java teams can organize concurrent downstream calls, improves virtual thread behavior, and extends startup optimizations. This is not a reason to flip every production service overnight. It is a reason to understand which bottlenecks Java 26 can remove, which features remain preview, and exactly what your benchmarks must prove. This SystemSignal visual breakdown focuses on the Java 26 changes that matter to backend teams. HTTP version 3, structured concurrency, virtual threads, startup and garbage collector improvements, plus the compatibility traps to test before rollout. The headline feature for network-heavy services is HTTP version 3, but the release has several backend implications. Structured concurrency reaches its 6th preview with a redesigned scope and joiner model. Ahead-of-time object caching can now work with any garbage collector, including ZGC, which broadens the startup story for latency-sensitive services. G1 reduces synchronization between application and garbage collector threads to improve throughput. Virtual threads can unmount from their carrier when waiting for another thread to initialize a class, removing a pathological source of pinning. Java 26 also warns when deep reflection mutates final fields, preparing applications for stricter integrity in a future release. Some items are ready for ordinary use, others require preview flags or migration work. HTTP version 3 keeps familiar HTTP semantics while changing the transport underneath. The client first learns that the destination supports HTTP version 3, often through configuration or an alternative service advertisement. It then creates a QUIC connection over UDP. QUIC combines transport security and multiplex streams, so the handshake and encryption model differ from TCP plus TLS. Independent request streams share the connection without making one lost packet block delivery on every other stream. At the edge, a load balancer or gateway terminates HTTP version 3 and usually forwards the request through the existing service network. Your application protocol may look familiar, but firewalls, observability, connection limits, retry behavior, and edge support all become part of the rollout decision. The most important deployment detail is easy to miss. Java 26 does not silently change the default client protocol from HTTP version 2 to HTTP version 3. Applications opt in. That restraint matters because protocol support is an end-to-end property. The Java client, DNS or alternative service discovery, enterprise firewalls, cloud load balancers, proxies, and destination server must all cooperate. A benchmark on a clean office network proves very little. Test mobile-style handoffs, packet loss, long-distance links, connection reuse, certificate negotiation, blocked UDP, and graceful fallback. Also inspect the dependencies surrounding the standard client. Frameworks and service SDKs may wrap it, pin protocol settings, or expose different pools. The right migration begins with one measured client path, not a global configuration change. HTTP version 2 already multiplexes many requests, but all of those streams ride one ordered TCP byte stream. When a TCP packet is lost, later bytes wait even if they belong to another HTTP request. QUIC moves stream management into an encrypted transport over UDP, allowing packet loss on one stream without imposing the same transport level delay on unrelated streams. QUIC also gives connections identifiers that are not defined only by the current IP address and port, enabling connection migration when a device changes networks. None of that guarantees lower latency for every backend. Stable data center links may show modest gains, while mobile and lossy paths may benefit more. HTTP version 2 also has broader operational maturity, so fallback remains essential. Now consider a backend request that needs a profile, recent orders, and a risk decision. Unstructured code can submit 3 tasks, keep 3 futures, and then assemble ad hoc timeout and cancellation logic. Structured concurrency treats those subtasks as children of one lexical scope. The parent forks the work, joins it through an explicit policy, and closes the scope before the request exits. If the response only needs the first successful result, the joiner can express that. If every dependency must succeed, failure can cancel siblings that no longer have useful work to perform. The runtime gains a tree that matches the developer's mental model: request, scope, and subtasks. That structure improves cancellation, failure handling, and observability together. Structured concurrency in Java 26 is the 6th preview, not a permanent API contract. Teams must compile and run with preview features enabled, and they must accept that source changes may be required in a later JDK. That does not make the idea irrelevant. It means production adoption needs an explicit policy. Keep the preview API behind a small application boundary, rather than spreading it through every controller and service. Test interruption, deadlines, cancellation, and partial failure, because those semantics are the reason to use the model. Virtual threads and structured concurrency solve different problems. Virtual threads make blocking tasks cheap enough to represent abundant concurrent work. Structured concurrency defines the lifetime and ownership of related tasks. Using one does not automatically provide the other. The difference is not merely syntax. With loose futures, a timeout in the request handler does not guarantee that every downstream operation stops. One forgotten task may continue consuming a connection, holding memory, or writing a result nobody will use. Exception handling becomes distributed across callbacks and join points. A structured scope establishes ownership. Children cannot quietly escape the lifetime of the parent scope. The join policy states what success means, and cancellation can propagate to sibling work. Monitoring tools can present related operations as a hierarchy rather than a flat collection of threads. This is especially valuable in fan-out APIs, aggregators, and orchestration services, where one incoming request creates many dependent calls, and where abandoned work becomes a production capacity problem. Some Java 26 improvements sit below application code. Ahead-of-time object caching can load cached objects from a garbage collector neutral format, allowing the mechanism to work with collectors beyond the earlier constraints, including ZGC. The goal is better startup and warm-up behavior. G1 reduces synchronization between application and garbage collector threads, targeting higher throughput. Virtual threads waiting for another thread to complete class initialization can now unmount from their carrier in most cases, freeing the platform thread for other work and avoiding a pathological form of scheduler starvation. These are promising changes, but aggregate benchmark scores hide trade-offs. Measure cold start, warm-up, allocation, pause behavior, throughput, P95 and P99 latency, carrier pinning, and CPU separately on the collector and workload you actually deploy. A safe rollout starts with inventory. Record runtime flags, garbage collectors, agents, bytecode tools, reflective libraries, TLS providers, native dependencies, and frameworks. Java 26 warns about deep reflection that mutates final fields, so expose those warnings in test and staging instead of suppressing them globally. Run compatibility suites before performance tests. Then benchmark representative traffic with protocol and runtime variables isolated. Compare HTTP version 2 and 3 through the real edge. Compare existing concurrency code with a small structured concurrency experiment. Canary the runtime separately from major application refactors so regressions have a narrow cause. Observe errors, handshake failures, UDP fallback, latency percentiles, garbage collection, carrier pinning, and startup. Promote only when measurements agree, and keep a tested rollback image. Java 26 changes the backend conversation in several useful ways. HTTP version 3 is now available through the standard HTTP client with minimal application-level change. But it remains opt-in because successful deployment depends on the complete network path. QUIC can reduce cross-stream blocking and preserve connections through network changes, yet the value is workload-dependent and fallback still matters. Structured concurrency offers a clearer ownership model for request fanout, coordinated cancellation, and task observability. But it remains a preview API and should stay behind a narrow boundary. Runtime improvements expand ahead-of-time caching, reduce G1 synchronization, and improve a virtual thread waiting case. But only production-shaped measurements can tell you what they mean for your service. Start with the current patched Java 26 build, inventory compatibility risks, benchmark one variable at a time, and use canaries with explicit rollback. The goal is not to adopt every feature. The goal is to remove a measured bottleneck without creating a new operational mystery. If you enjoy clear explanations of complex engineering problems and important developments in technology, subscribe to SystemSignal. We publish a new visual breakdown every week.